Hey, Willie, I've been taking those readings on the feed water system like you told me, but I'm not sure this one's right. Can you take a look at it for me?
Sure, Tom. Let's take a look and see what you got. I've never seen this temperature reading so high.
Oh, you can tell that just by looking at it.
Sure, but I've got 20 years of looking at them. Here, let me show you how you can check it for yourself.
All right.
A 20-year veteran of a power plant can usually look at the reading indicated on an instrument and from his experience tell if the reading is right or wrong. Now, the chances are pretty good that you don't have 20 years experience to draw on, but you still need to be able to check readings and make sure that the reading you get is proper for the system or equipment that you're checking. Where can you find this information? Well, one of the best sources that you can use are the steam tables. Traditionally, the steam tables consist of 3 separate tables of information that can give you the values for the properties of saturated water and steam. Table 1 is entitled Saturated Steam Temperature Table. Table 2 is Saturated Steam Pressure Table. And Table 3 is Superheated Steam. In addition to these 3 tables, there is usually additional information available in the steam tables that we'll be discussing later on. For now, we'll concentrate on the information available in Tables 1 and 2. In order to use the tables accurately, you have to know something about the process that you're checking. There are basically 3 things that you'll need to know: the temperature, the pressure, and whether the process is saturated or unsaturated. If you know 2 of these properties, the steam tables can give you the 3rd piece of information. Another thing that you need to keep in mind is that the values for pressure in the steam tables are given in pounds per square inch absolute. The gauges in your plant usually will display pressure readings in pounds per square inch gauge. So it's necessary to convert the gauge pressure reading to an absolute pressure reading in order to use the tables. As you know, to convert a gauge value to an absolute value, you add the value for atmospheric pressure to the gauge value. The final thing you should keep in mind is that the examples we'll be using are typical of a power plant. The actual conditions in your plant will probably be different. Let's begin by seeing how the steam tables are organized. For your convenience, we've included a copy of the steam tables with your textbook. You should take a look at the tables after watching this segment. Table 1, Saturated Steam Temperature Table, looks like this. It's organized in a series of columns that give information on temperature, specific volume, enthalpy, and a property that may not be familiar to you, entropy. The first column in Table 1 indicates temperature in degrees Fahrenheit. The heading on the column also shows the symbol used to indicate temperature, a small letter T. For our example, we'll use a temperature that should be familiar to you, 212 degrees Fahrenheit. Next to the temperature column is a column headed Absolute Pressure Pounds per Square Inch. The small letter P symbolizes pressure. In our example, 14.696 psia, or as we've rounded it off, 14.7 psia, is the saturation pressure for steam at 212 degrees Fahrenheit. The next 3 columns come under the heading Specific Volume and give information about the specific volume of saturated water and steam at various temperatures and pressures. The units used in each of these columns are cubic feet per pound. The first column under specific volume indicates the specific volume of saturated liquid. The symbol for this is V with a subscript F. The specific volume for saturated water at 212 degrees Fahrenheit and 14.7 psia is 0.016719 cubic feet per pound. We'll skip the second column under specific volume for now and look at the third column. This column is headed Saturated Vapor and symbolized by a V and the subscript G, meaning gas. The value in this column is the specific volume of saturated steam at our given temperature and pressure. It's 26.799 cubic feet per pound. The subscripts F and G may seem a bit confusing since a gas is generally considered to be a type of fluid. In the steam tables, however, F refers to a fluid in a liquid state, and G refers to a fluid in a gaseous state. Now, it is often useful to know the amount of change in specific volume that takes place when water is completely boiled to steam. The middle column under the specific volume heading gives you this information. This column is headed evaporation and is symbolized by the letter V and the subscript Fg. The value given in this column is the difference between the specific volume of saturated steam and saturated liquid. The value for 212 degrees Fahrenheit at 14.7 psia is 26.782 cubic feet per pound. Next to the columns for specific volume are three similar columns under the major heading of enthalpy. As you know, enthalpy is the thermal energy or heat content in a pound of a substance. Like specific volume, the values for enthalpy are different depending on the state that the water is in. The first column under enthalpy is labeled saturated liquid and is symbolized by the small letter H and the subscript F. The values indicated are in units of BTUs per pound. The value for saturated water at 212 degrees and 14.7 psia is 180.17 BTUs per pound. We'll skip the center column under enthalpy for the time being and take a look at the third column. This column is headed saturated vapor and is symbolized by the small letter H and the subscript G. The values in this column are the heat content of saturated steam. For 212 degrees at 14.7 psia, the enthalpy of saturated steam is 1,150.5 BTUs per pound. As you know, when water is heated to its saturation temperature and begins to boil, additional heat added to the steam-water mixture does not increase the temperature of the mixture. The additional heat, the latent heat of vaporization, serves to cause the change in state from water to steam. The center column under the enthalpy heading is labeled evaporation and symbolized as H with the subscript Fg. This column represents the difference between the enthalpy of saturated water and saturated steam, or more simply, the latent heat of vaporization. For our example, the latent heat of vaporization for 212 degrees and at 14.7 psia is 970.3 BTUs per pound. The next major heading after enthalpy is entropy. Entropy is a property that can get extremely confusing. Basically, entropy is a calculated property that is used to evaluate the efficiency of a process. Entropy is indicated in units of BTUs per degree Fahrenheit per pound, although you may see it indicated in units of BTUs per degree Rankine per pound. The Rankine temperature scale is another scale that can be used to measure temperature. Although its actual numerical values are different, the size of a Rankine degree is exactly equal to a Fahrenheit degree. So, for our purposes, it doesn't matter whether we use Fahrenheit or Rankine. Like specific volume and enthalpy, there are three columns under the entropy heading. Again, these columns indicate the values for saturated liquid, symbolized by the small letter S sub F. The values for saturated vapor, S sub G, and the evaporation or difference between S sub F and S sub G, symbolized by S sub Fg. The final column in Table 1 repeats the temperature in degrees Fahrenheit. The importance of this column should not be overlooked. When reading across columns of numbers, it's easy to lose your place or slip down a line or two. Having the temperature on either side of the table lets you make sure that you're reading the right line. Now that we've looked at Table 1, let's take a quick look at Table 2, entitled Saturated Steam Pressure Table. In this table, you have the values for the conditions associated with pressure. Table 2 is arranged in a similar manner as Table 1, except for the first two columns and the last column. The first major heading in Table 2 is absolute pressure in units of pounds per square inch. Again, the symbol used in this column to identify pressure is the small letter P. We'll use atmospheric pressure, 14.696 or 14.7 psia as our example. The column next to the absolute pressure column is temperature in degrees Fahrenheit. As you would expect, the saturation temperature for water at atmospheric pressure is indicated as 212 degrees Fahrenheit. The next three major headings are specific volume, enthalpy, and entropy. As in Table 1, each heading has three columns under it designated as saturated liquid, evaporation, and saturated vapor. Similar information is given in these columns in Table 2 as is given in the columns in Table 1. The major difference between the values given in Table 2 are that they are listed according to pressure. The final column in Table 2 repeats the absolute pressure in pounds per square inch. As in Table 1, it is easy to lose your place when reading across the various columns, and the final column helps you make sure that the values are taken from the right place. In the next segment, we'll use these tables to solve some problems. For now, let's quickly review what we've covered so far. We said that the purpose of Tables 1 and 2 of the steam tables is to give you information about the properties of water and steam at various temperatures and pressures. In order to accurately use the tables, you need to know two of three things about the process you're dealing with: the temperature and the pressure, and whether the conditions are saturated or not. Knowing any two of these conditions will allow you to find the third, as well as specific volume, enthalpy, and entropy. Take some time to read over the material in the text and familiarize yourself with steam tables and answer the questions at the end of the segment.
How are you doing checking those readings for the steam tables, Tom?
Well, I'm doing pretty well, Willie, but one thing I don't understand, and that's if these tables only show the properties of saturated water and saturated steam, what do I do when I have subcooled conditions like I'm supposed to have in this condensate pump?
Well, if you're willing to accept a close approximation, you can still use steam tables.
Oh?
Here, let me show you.
Our young operator here has posed a very good question. If the steam tables only indicate the properties of saturated water and steam, how can you find out about the conditions of subcooled water? Well, let's see. We'll use as our example typical conditions at the discharge of the condensate pump that we looked at in the last unit. We said that at the discharge, the temperature of the condensate is 102 degrees Fahrenheit and the pressure is 205 psia. Now, since we know both the temperature and the pressure of the process that we're discussing, we can use either Table 1 or Table 2. To start, let's use Table 1. We'll start by finding the temperature in Table 1, 102 degrees Fahrenheit. There it is. Now we look at the pressure column and find that the saturation pressure for water at 102 degrees is 1.00789 psia. We'll round that off to 1 psia to make things easier. What this means is that when you have water at 102 degrees and 1 psia, it is saturated. But as you learned in an earlier unit, if pressure is above the saturation pressure, then the water will be subcooled. So, since our indicated pressure is 205 psia, more than 200 pounds per square inch higher than the saturation pressure, the feed water at the discharge of the condensate pump is subcooled. Now you can find out something else about the feed water at the discharge of the pump. It's enthalpy. As you'll recall, the enthalpy of subcooled water doesn't change substantially with changes in pressure. So, if you follow the line at 102 degrees across to the enthalpy column for saturated liquid H sub F, you'll see that the enthalpy of the subcooled water is 69.995 BTUs per pound. That's very close to the enthalpy value of 70 BTUs per pound that we gave in the last unit. Now, while the enthalpy value is not exactly correct, for all but very precise calculations, it's close enough for work in the plant. Now, it's possible to figure the amount of subcooling in the condensate. Again, we'll calculate this using Table 1. If we go down the absolute pressure column until we find the pressure at the outlet of the condensate pump, 205 psia, we can find the saturation temperature for water at the indicated pressure. Now, we don't find exactly 205 psia in this column, but do find a close approximation, 205.294 psia. Since all we need is an approximate value, 205.294 psia is close enough for our purposes. Looking over at the temperature column, we see that the saturation temperature is 384 degrees Fahrenheit. If we subtract our existing conditions, 102 degrees, from the saturation temperature at 205 psia at 384 degrees, we'll have the approximate amount of subcooling. The difference is 282 degrees. This means that the water at the discharge of the condensate pump is about 282 degrees below its boiling point. So there's approximately 282 degrees of subcooling at the discharge of this pump. Now, as we said earlier, we can get the same information from Table 2. Let's check the amount of subcooling using Table 2. Since Table 2 doesn't indicate the properties of water and steam associated with every pressure, we don't find the exact value we're looking for, 205 psia. Instead, we find pressures of 200 psia and 210 psia. All is not lost, however. We can still figure the approximate value with a few simple calculations. The saturation temperature given for 200 psia is 381.80 degrees Fahrenheit, and the saturation temperature for 210 psia is 385.91. Since the value for 205 psia occurs halfway in between, if we add the two values for temperature together and divide by 2, we'll get the approximate saturation temperature for water at 205 psia. For our calculations, we'll round off 381.80 to 382, and 385.91 to 386. Adding these values together, we get 768. Dividing 768 by 2, we get 384 degrees Fahrenheit as our answer. This is the same saturation temperature we found using Table 1. All right, if we subtract our actual temperature, 102 degrees, from our saturation temperature, 384 degrees, we find that the amount of subcooling is 282 degrees. Again, the answer is the same as the one we calculated earlier. We got the same answer regardless of the table we used. However, I think you'll agree that in this case, Table 1 was easier to use. As a general rule, it's best to use the table that you feel most comfortable with, or the table that has values closest to the ones you need. Let's take another example so that we can get some practice using the tables. For this example, we'll use the conditions at the outlet of a typical boiler drum. Steam leaves the boiler drum at about 2700 psia. Now we know that saturation conditions exist in the boiler drum, so what we need to find is the temperature of the steam. The easiest way to find this is to use Table 2. Looking down the absolute pressure column in Table 2, we find exactly 2700 psia, so we won't have to make any calculations. Moving across to the temperature column, we find that the saturation temperature at 2700 psia is 679.53 degrees Fahrenheit. Now, if we want to know the enthalpy of saturated water at this temperature and pressure, we can continue across the columns until we reach the column under enthalpy entitled Saturated Liquid H sub F, and we find the value is 757.3 BTUs per pound. In the same manner, we can find the enthalpy of saturated steam if we check the saturated steam column H sub G. It's 1069.7 BTUs per pound. And if we need to know the amount of heat needed to change saturated water completely into saturated steam, the latent heat of vaporization, we check the column headed evaporation H sub FG and find that we need 312.3 BTUs per pound. If you take the time to actually calculate the difference between H sub F and H sub G, you'll find that the value determined this way doesn't exactly equal 312.3 BTUs per pound. The reason for this is that while the values in the steam tables are quite accurate, in some cases it is necessary to round them off. The mathematical rounding accounts for the minor discrepancy. Using Table 2, we can find similar information about the properties of specific volume and entropy by checking the appropriate columns in the table. In this segment, we've shown you how you can use tables 1 and 2 of the steam tables to find information about the properties of saturated water and steam. We've also shown you that if you're willing to accept approximate values, you can also find some information about subcooled water in the tables. The steam tables are a valuable tool for finding the properties of water and steam and the state of water in your plant. In the next segment, we'll look at how to use Table 3, superheated steam. For now, read over the material in your text and answer the questions. If you're having any trouble following this material, ask your instructor to help you. So far in this unit, we've concentrated on tables 1 and 2 of the steam tables, those that deal with saturated water and steam. You've also learned that close estimates of the properties of subcooled water can be found in these tables as well. The third table that we need to cover is Table 3, superheated steam. Table 3 gives you information about the properties of superheated steam, but it's organized differently than the tables we've looked at so far. We'll use atmospheric pressure as our example again. Table 3 consists of headings for absolute pressure, saturated water, saturated steam, and then has columns for temperatures in degrees Fahrenheit. To use this table, you first find the pressure that you need. In our case, it's 14.696 psia. Notice that underneath the pressure value, the saturation temperature is indicated in parentheses. Next to the pressure value are 4 letter designations, SH, V, H, and S. As you probably know, these stand for superheat, specific volume, enthalpy, and entropy. Directly across from each of the letters is the value for saturated water at the given temperature and pressure. At 212 degrees Fahrenheit and 14.696 psia, there is no superheat, so no value is indicated. However, there are values for specific volume, enthalpy, and entropy. Next to the values for saturated water are the values for saturated steam. Again, we have no value for superheat at the saturation temperature, but we do have values for specific volume, enthalpy, and entropy. From here on, we can read the values for superheat, specific volume, enthalpy, and entropy directly from the tables. Notice that since the first temperature column is 200 degrees, a temperature below saturation for water at 14.696 psia, no values are given. But from 250 degrees Fahrenheit on up, we have values. At 250 degrees Fahrenheit, the amount of superheating that has occurred is 38 degrees. This means that the temperature of the steam is 38 degrees higher than the saturation temperature. The specific volume of the superheated steam at 250 degrees is 28.42 cubic feet per pound. Enthalpy is 1168.8 BTUs per pound, and entropy is 1.7833 BTUs per degree Fahrenheit per pound. Now, Table 3 is more complicated than the other tables, but it is important for your understanding of the properties of superheated steam. From what you've learned so far, you should be able to help our young operator solve this problem.
Oh, I'm glad you showed up. I need to find out the enthalpy of steam at the outlet of the boiler. And I know that its temperature is 1,000 degrees Fahrenheit, and its pressure is 2450 psia, but I can't find it in either Table 1 or Table 2.
That's because the process is superheated, so you have to use Table 3. Turn back over to the superheated Table 3.
While Willie is showing our young operator how to solve the problem, let's you and I do it together. We know that the process is superheated and that the temperature is 1,000 degrees Fahrenheit at 2,450 psia. We look down the absolute pressure column in Table 3 for 2,450, and we find that only the values for 2,400 psia and 2,500 psia are given. So we'll have to do some calculating. The first thing we need to find is the values for enthalpy at 1,000 degrees at 2,400 psia and 2,500 psia. we look across the line marked enthalpy at 2,400 psia and under the column headed 1,000 degrees. We find the value for enthalpy to be 1,460.9 BTUs per pound. Doing the same thing for the line marked 2,500 psia, we find its enthalpy value is 1,457.5 BTUs per pound. Now that we know the enthalpy values, we can do some simple calculations. Since 2,450 psia is the pressure we want, an enthalpy value 4, and it's halfway between 2,400 and 2,500 psia, adding the two known values together and dividing by 2 will give us our answer. 1,460.9 BTUs per pound plus 1,457.5 BTUs per pound gives us a total of 2,918.4 BTUs per pound. Dividing this by 2, we get 1,459.2 BTUs per pound as the enthalpy value for steam leaving the boiler at 2,450 psia and 1,000 degrees Fahrenheit. Let's hope that our young operator got the same answer. Since this last example wasn't too difficult, let's try another one. We want to know the enthalpy of the steam leaving the high pressure section of this turbine. We know that the outlet conditions are 460 psia at 680 degrees Fahrenheit. We look through Table 3 until we find the desired pressure, 460 psia. Directly under the pressure value is the saturation temperature for 460 psia. It's 458.5 degrees Fahrenheit. Since our outlet temperature is 680 degrees Fahrenheit, and this is higher than the saturation temperature, we know the process is superheated. Now, the next step is to find the enthalpy value for that outlet temperature. We're not going to find the exact temperature we need because the columns don't give every possible value. However, we can find the values for 460 psia at 650 degrees and 700 degrees. And with this information, we can calculate a value for 680 degrees. At 460 psia and 650 degrees Fahrenheit, the value for enthalpy is 1,331.8 BTUs per pound. Enthalpy at 460 psia and 700 degrees is 1,360 BTUs per pound. Our given temperature, 680 degrees Fahrenheit, is 3/5 of the way between 650 and 700 degrees. So, if we find the difference between the enthalpy values of the known temperatures and take 3/5 of it, then add that amount to our lowest value, we'll get the value we're looking for. Now, the procedure is more difficult to say than it is to do, so let's work through the problem together. The difference between the value for enthalpy at 460 psia at 650 degrees, 1,331.8 BTUs per pound, and the enthalpy at 460 psia at 700 degrees, 1,360 BTUs per pound, is 28.2 BTUs per pound. Now, since the value we're looking for is 3/5 of the way between 650 and 700 degrees Fahrenheit, we have to find 3/5 of 28.2 BTUs per pound. This works out to be 16.9 BTUs per pound. To find the enthalpy of superheated steam at 460 psia and 680 degrees Fahrenheit, we add 16.9 BTUs per pound to the value for enthalpy at 650 degrees. 1331.8 BTUs per pound plus 16.9 BTUs per pound equals 1348.7 BTUs per pound. This is the enthalpy of superheated steam at 460 psia and 680 degrees Fahrenheit. Okay, we've been using Table 3 to determine the properties of superheated steam. Even though Table 3 is a bit more complicated than the tables we've looked at before, it is an important tool for finding the properties of superheated steam in your plant. Before we go on to look at another example, read the material in your text and answer the questions. Your instructor can help you clear up any problems you might have with Table 3. You've now had a chance to look at Table 3 and study its organization. Let's look at one more example of how Table 3 can be used to determine enthalpy at a given pressure and temperature. Then we'll go on to look at the conversion factors that are found in some steam tables. The steam at the outlet of a typical reheater is superheated, and it leaves the reheater at around 435 psia at a temperature of around 1,000 degrees. Looking at Table 3, we find that the exact enthalpy value for the pressure we have is not listed. Instead, we find the values for 420 psia and 440 psia. This means that in order to find the value for 435 psia, we have to do some calculating. The enthalpy at 420 psia and 1,000 degrees is 1,522.7 BTUs per pound. The enthalpy value at 440 psia and 1,000 degrees is 1,522.1 BTUs per pound. The difference in enthalpy between these two values is 0.6 BTUs per pound. 435 psia is 1/4 of the way from 440 to 420 psia. So we have to find 1/4 of the value of 0.6 BTUs per pound. This works out to be 0.15 BTUs per pound. In order to maintain the proper proportions, we have to add 0.15 BTUs per pound to the enthalpy value of 440 psia at 1,000 degrees, 1,522.1 BTUs per pound. This gives us the value for enthalpy at 435 psia and 1,000 degrees. It's 1,522.25 BTUs per pound. Okay, you've now learned how to use all three tables and how to calculate values that are not listed in the tables. Let's go on and look at the conversion factors that are included in some steam tables. As you know, throughout this program we've often needed to convert from one unit to another in order to find information about the plant cycle in a form that we could use. Conversion factors give us a quick reference for converting between units. For example, let's say that we know that this storage tank holds 2,000 gallons of water. Well, for whatever reason, say we need to know how many cubic feet are occupied by the 2,000 gallons of water in the tank. We could calculate the number of cubic feet by determining the dimensions of the tank and the height of the water, or we can turn to the conversion factor. If we search through the conversion factors, we find a listing for converting gallons to cubic feet. According to the conversion factor listed in our steam tables, if we multiply the number of gallons by the conversion factor, 0.13368 cubic feet per gallon, we'll get the answer we're looking for. Doing this, we find that 2,000 gallons of water occupies a volume of 267.36 cubic feet. There are many other conversion factors that are useful in the day-to-day operation of your plant. Other conversion factors that apply specifically to your plant will not be listed in the steam tables, as our young operator is about to find out.
Hey, hi, Willie. Listen, something happened yesterday that I didn't really understand. Everybody seemed all upset about a loss in superheat.
That's right. 5 degrees low on the number 2 unit yesterday.
5 degrees, what's the big deal? Does that mean our outlet conditions are 995 instead of 1,000?
Loss of 5 degrees temperature is an awful lot of money.
Money?
Money.
You're not going to tell me I can figure this out from using the steam tables, are you?
Well, not exactly, but 5 degrees loss of temperature means an awful lot of kilowatts. Here, let me show you.
All right.
What Willie is going to show our operator is how to use the steam tables and conversion factors to convert the 5-degree loss in superheat to kilowatts. And then, using the cost for producing a kilowatt in his plant, they'll figure out a dollar and cents answer. This is something that you may want to do for your plant. It will give you a good idea of just how useful the steam tables can be and why you need to be careful to operate your plant as efficiently as possible. We'll use the superheater outlet conditions of a typical boiler to show you how to set up this problem. Earlier, we determined that the enthalpy of steam leaving a typical boiler at 2,450 psia and 1,000 degrees Fahrenheit was 1,459.2 BTUs per pound. By using the steam tables and following a procedure similar to the one we used before, we can calculate the enthalpy at 5 degrees less. We've already done this for you, and at 2,450 psia and 995 degrees Fahrenheit, the enthalpy of the steam is 1,456 BTUs per pound. The difference between these two values is 3.2 BTUs per pound, which is the loss we're concerned with. Now, let's determine how many BTUs per hour are lost in a 5-degree loss in superheat. To do this, we multiply the number of BTUs per pound by the number of pounds of steam that flows to the turbine every hour. This is about 1.3 million pounds per hour in the plant we're talking about. This works out to be 4,160,000 BTUs per hour, which are not reaching the turbine when there's a 5-degree loss in superheat. Now, something that the steam tables don't tell you is that even if these 4,160,000 BTUs per hour were reaching the turbine, typically only 80% of it would be converted to electricity. You can find out the exact figures for your plant, but we'll use this typical value in our calculations. To find out how many BTUs per hour are actually being lost in a 5-degree loss in superheat, we need to take 80% of 4,160,000. That works out to be about 3,328,000 BTUs per hour in a 5-degree loss in superheat. All right, we know how many BTUs are lost in 1 hour, but we don't sell electricity by the BTU. We sell it by the kilowatt hour. To find out how many kilowatt hours are in 3,328,000 BTUs, we have to use the conversion factors in our steam tables. Looking for the conversion factors, we find that to obtain kilowatt hours from BTUs, we need to multiply the BTUs by 0.000293. So, multiplying 3,328,000 BTUs per pound by 0.00293, we find that about 975 kilowatt hours are lost when the steam temperature is 5 degrees low for 1 hour. Now, if you take this number and multiply it by your cost per kilowatt, you'll see just how significant a 5-degree loss in superheat is in terms of dollars and cents. Well, you've now seen how to use tables 1, 2, and 3 in the steam tables, and how to use conversion factors that are listed in some steam tables. You've also seen how the tables and conversion factors can be used to calculate how much a loss in superheat temperature represents in dollars and cents. In the next segment, we'll look at one more item that is often found in steam tables, the Mollier diagram. This diagram can give you a great deal of information if you learn how to use it properly. For now, though, take some time to read over this material in your text and answer the questions. If you need help with this material, your instructor is there to assist you.
Well, looks like you're getting a lot of use out of the steam tables. What are you up to now?
Well, I thought I would figure out some of the basic conditions in the plant so I had a better understanding of what was going on.
That's a good idea, but you can save yourself an awful lot of trouble and do a lot less calculations if you'd used the Mollier chart.
You mean this thing in the back of the book? No thanks, Willie. I don't think I could ever figure this out. Okay.
Well, it takes some patience, and you have to have some knowledge. But if you work at it, you can save yourself an awful lot of trouble.
Well,
if you've taken a look at the Mollier diagram in your steam tables, your first reaction was no doubt very similar to our young operators. At first glance, the Mollier diagram seems very confusing, and you might wonder how anyone could make sense out of all these converging lines. However, by learning the basics of how the Mollier diagram is organized, you'll find that you can read a number of values directly from the diagram without having to do a lot of calculations or going into the steam tables. In general, all the Mollier diagram is a graph of some of the information found in the steam tables. The Mollier diagram is limited to the properties of steam. You can find information about temperature, pressure, moisture content, enthalpy, and entropy. You cannot find any information about specific volume on this graph. We'll look at how the Mollier diagram is set up and how to find basic information. In the next segment, we'll look at some specific uses of the diagram. To begin with, the Mollier diagram is a graph of entropy versus enthalpy. Entropy, as you know, is a calculated property used to evaluate the efficiency of a process. The units for entropy used on this diagram are BTUs per degree Fahrenheit per pound. Enthalpy is the heat content of the water or steam and is measured in BTUs per pound. This line, labeled the saturation line, divides the graph into two regions. The region above the saturation line is the superheated region, and the region below the saturation line is the wet steam region. That is, the steam in the wet steam region contains moisture. The wet steam region is basically the transition zone that we talked about in an earlier unit. The transition zone, you'll recall, is where water and steam can coexist. Running diagonally from the lower left to the upper right of the graph are lines that look like this and indicate constant pressure in pounds per square inch absolute. The line indicating atmospheric pressure is a broken line which distinguishes it from the other lines of constant pressure. If you need to determine the enthalpy of any point on the saturation line, you simply find where the appropriate pressure line and the saturation line intersect and trace it out to the edge of the graph where enthalpy is indicated. For example, if you need to know the enthalpy of steam at saturation temperature and atmospheric pressure, you follow the saturation line until it intersects with the pressure line at 14.696 psia. Then you follow the enthalpy line out to the edge of the graph. Using this method, you find that the value for enthalpy is a bit more than 1,150 BTUs per pound. In actuality, the enthalpy value given in the steam tables is 1,150.5 BTUs per pound. For most purposes, the approximate value from the Mollier diagram will be close enough. Another thing that you should know about the constant pressure lines is that at pressures lower than atmospheric, pressure is indicated in both psia and inches of mercury. This is simply a convenience for the operator, since pressure lower than atmospheric is often indicated in inches of mercury. Showing both scales on the Mollier diagram keeps you from having to convert between the two units. These values are often here on the diagram. Other lines in the wet steam region of the graph run like this and indicate the moisture content of the steam-water mixture in percent moisture. You can find the moisture content that you need to know and the pressure and enthalpy of the mixture. At 1400 psia and an enthalpy of 1,115 BTUs per pound, for example, we see that the lines intersect here at about 10% moisture content. Being able to read this type of information directly from the Mollier diagram can save you from having to make calculations like we did in Unit 1. Above the saturation line, there are lines that run this way and indicate constant temperature in degrees Fahrenheit. Other lines running in this direction basically follow the same shape as the saturation line and indicate constant superheat, also in degrees Fahrenheit. If you need to know the amount of superheat in steam at 2,450 psia and 1,000 degrees, you find where the pressure temperature lines intersect and see that the intersection falls between 320 and 340 degrees Fahrenheit. Taking the average, you can determine the amount of superheat, which is about 330 degrees. Now, what we've just shown you is general information that can be found on the Mollier diagram or in more detail in the steam tables. If all you need are close approximations of the values for the properties of steam, then the Mollier diagram allows you to read the information directly. If you need more precise values, then you'll have to consult the steam tables. Now, in addition to the information that we've just shown you, using the Mollier diagram, you can actually plot the transfer of energy at various points in the plant cycle. The Mollier diagram can also be used to determine how efficiently a plant is operating. In the next segment, we'll look at some other aspects of the Mollier diagram. At this point, however, you should stop the tape and read the material in your text. In the last segment, we showed you how to find information about the properties of steam using the Mollier diagram. We also told you that the Mollier diagram is simply a graph of part of the steam tables which can show you the transfer of energy in various components in the plant cycle. In this segment, we'll take a look at how the Mollier diagram can be used to find out about energy transfer by using the outlet conditions that we established for various points in a typical plant cycle in Unit 2. We said that feed water entering the boiler is heated to the saturation point and then boiled. Boiling causes the water to change state from a liquid to a gas. Then, as additional heat is added to the saturated steam, its heat content, or enthalpy, increases, making the steam superheated. In the last segment, we plotted the outlet conditions of the boiler at 2,450 psia and 1,000 degrees Fahrenheit, and found that there was about 330 degrees of superheat. If we trace the intersection of our values for temperature and pressure out to the enthalpy values on the edge of the diagram, we find that enthalpy at this point is about 1,459 BTUs per pound. Now, as the steam leaves the boiler and passes through the blades in the high-pressure turbine, some of its energy in the form of heat and pressure is converted to mechanical energy, resulting in a decrease in the pressure, temperature, and enthalpy of the steam. At the outlet of the high-pressure turbine, pressure has decreased to 460 psia, and temperature has dropped to 680 degrees. Plotting these points on the Mollier diagram, we can read the enthalpy value at the outlet at around 1,349 BTUs per pound. Taking the difference between these two values, we discover that approximately 110 BTUs per pound was removed from the steam by the HP turbine. In this cycle, before the steam is sent to the IP turbine, it is sent back to the boiler for reheating. The outlet conditions at the reheater are 435 psia and 1,000 degrees Fahrenheit. The 1,000 degrees temperature line and the 435 psia pressure line intersect at this point on the Mollier diagram. To find out how much heat is added to steam in the reheater, we take the difference in enthalpy between the outlet conditions at the reheater here and the outlet conditions of the HP turbine here. At the outlet of the HP turbine, the enthalpy is approximately 1,349 BTUs per pound. Enthalpy at the outlet of the reheater is approximately 1,522 BTUs per pound. The difference, then, is 173 BTUs per pound. This means that 173 BTUs are transferred to every pound of steam as it passes through the reheater. After the steam passes through the IP and LP sections of the turbine, it is exhausted into the condenser at 1 psia and 102 degrees Fahrenheit. To find out how much energy is removed from the steam as it passes through the IP and LP sections, we first plot the conditions 1 psia and 102 degrees and find the difference in enthalpy between the outlet conditions of the reheater and the outlet conditions of the LP turbine. We already know the enthalpy at the outlet of the reheater. It's about 1,522 BTUs per pound. Checking the Mollier diagram, we find that the enthalpy at the outlet of the LP turbine is 1,105 BTUs per pound. This means that approximately 417 BTUs per pound are removed by the rest of the turbine. As you've probably realized, the steam tables, including the conversion factors and the Mollier diagram, are indispensable references for determining the properties of water and steam at various temperatures and pressures in the plant.
Can you help me?
Well, sure. What we got?
I'm not sure that I'm getting the proper reading from that pressure gauge. What should I do?
Well, let's see. You've got the temperature, and you know conditions are saturated. We can look the pressure up in this table.
Read over the remaining material in the text and answer the questions.